All right, you guys, we shall get started. So first off, we'd like to thank our sponsors here. If you want to be thanked next time as well, you can give us some money. We'll put your logo up there. If it's personal donation, I think we could probably put a photo in as well, I think. I think it has to be like a certain amount though. Yeah, and so without further ado, so this is Yehlin Cho, comes all the way from the other side of the river at MIT. I was trying to think of a fun fact, and I think the only thing I could think of is Yehlin is part of a K-pop band. Yeah. So apparently got disbanded recently, but maybe with some additional funding, you can bring it back together. Yeah. All right. Well, I think that's all I have to say. Oh, are you taking questions asked during?
Yep.
Oh yeah, so if anyone has questions, feel free to ask during. If you raise your hand, I can also pass on mic to you. Yep.
Okay. Hi, can you hear me? Yeah. Hi, thanks everyone to come to see my presentation today. Yeah, I'm Yehlin. I'm a fifth-year grad student working in Sergey at MIT. I'm working on protein design, like protein stability prediction, a lot of like cool things about the protein. And yeah, and also like it's my honor to like give a talk today as a like last seminar of like this BPDMC seminal series. So yeah. I'm really happy about this presentation today. Yeah, today I'm gonna give a talk about my two recent work, which is protein design and BoltzDesign and protein hunter. So this is like totally fine-tuning free method. So it actually uses a lot of like different AlphaFold3 style structure prediction models. So I mainly like focus on how AlphaFold3 style structure prediction models can be used for protein design. So as you already know, protein design is really universal. So it can serve any really many different roles. So it can like sometimes reactivate the immune system, like sometimes neutralize the allergen effect, and like sometimes can serve a new chemistry. So like a lot of enzymes are like solving a new chemistry and a lot of like signal like processing. I think there are like so many existing protein design method nowadays, and then you guys pretty like. I think you guys are pretty familiar with bind trap method. And then this is actually a really cool method using a backpropagation of AlphaFold2 model actually designs a really cool like picomolar de novo binder toward this PDL1 binder and also other many cool different like protein targets. I think, yeah, like we really solve many cool problems like for like recent 5 years, but I think there's definitely still like some problem we haven't really solved yet. And I think, yeah, like for example, this like TNF alpha proteins like are having this oligomeric protein structure. So it has like these three different like proteins are involving into like making this whole like complex. So last year, Alpha Proteo showed presented their new work, like showing a really high experimental success rate on like different cool targets. But actually, as you can see in the right part, the binder success rate on this TNF alpha protein was like almost like a 0%. I think it's generally hard to design a binder toward this oligomeric protein because it has a very clear binding binding interface, like which is like mainly like hydrophobics in this case. But if you generate the binder like toward this like one copy of protein, a lot of time this design method just make a protein that can bind to this like homoligomeric interfaces. So it's not really easy to handle this kind of protein. And also a lot of like enzyme is working in with the oligomeric states. So for example, this isomerase protein has an active site on the interface of these two protein copies. So to actually redesign this protein from the scratch, you need to like consider the dynamic of the single protein, but also the interaction between these two copies of proteins. So I think there are like still a lot of like challenging problems. This year, like I actually really wanted to focus more on like protein design problem. So I just like define like relatively easy to hard problems by myself. So I think if you have very well-defined protein and a protein interface, you definitely know where's the binding interface, and this is the hydrophobic interface. And if you have a lot of information like this PDB analogs, I think it's relatively easy to design the binder because you know where the binder should go. And also the static enzymes, for example, that has a very enriched evolutionary data set is also relatively easy to design because like you can always like fix the active site, like fix the conserved residue and redesign rest part of it. But I think there are like a lot of like medium level problems. Like still like before AlphaFold 3 came out, it was relatively challenging to design proteins toward a small molecule or nucleic acid binders. And also, as I mentioned, targeting multimeric proteins is also very challenging. And some proteins showing a very dynamic motion. But if you can like still get some information from experimental data point or simulation, yeah, you can probably get some hint from that. And definitely there are a lot of like hard problems. Yeah, in a biological system, like if your protein is highly dynamic, if your protein is working with a lot of like different cofactors or like multiple of different ligands, it's relatively hard because you need to like design something with a multiple different of ligands. And as I mentioned, like some proteins, the function emerges from the protein-protein interaction. So you need to like care all of this environment instead of like just thinking about this single protein. So yeah, after AlphaFold 3 came out, I actually really wanted to solve a lot of like the cool problems like related to small molecule binder design and nucleic acid binder design. So before going into details about my new method, I want to like talk a little bit about the AlphaFold 3 model. AlphaFold 3 model is like it came out last year. AlphaFold 3 can predict the structure of all atom biomolecules. So it's relatively similar to AlphaFold 2, but given as like sequence, MSA, and template as an optional as input, and MSA and the pair module process all the like, evolutionary information and the pairwise, global pairwise information using this pair module, and like getting that pair representation and single representation as an input. Diffusion model actually starting from the random noise, it denoise the all atom 3D coordinates into this like disorder structure representation. So the output of this diffusion model is XYZ coordinate, but also you can get the confidence score similar to AlphaFold 2 model. So you can get both sidewise confidence score like PLDT and this pairwise confidence score like PAE score. So you guys definitely know the bind prep paper and a lot of like Tia Rosetta related papers. So this is not a like totally new concept, but we also came up with this idea. Can we actually use the structure prediction model for design purposes? So the key idea is like very simple and very similar to the previous method. So we thought to design a protein, all you need is contact loss and the confidence matrix. So like imagine you have a real like sequence and the sequence that actually folded into good structure. If you input the sequence into the model will like give you a highly confident structure and a score. But if you give any random like sequence or like highly like disordered sequence, you'll get the very poor structure and the like low confidence score. You can actually use this like confidence score and the context score as a loss function of your optimization. So starting with the like random like sequence, you would predict something and get the output score as a loss function backpropagated back to the input sequence instead of updating the loss. So you're doing you can do the gradient optimization. So starting with a random sequence, optimize it until you get a highly confident structure and a confidence score. So then like some of the people might ask, how can you actually optimize this? Like because the gradient optimization is like based off the soft gradient, but protein amino acid sequence is discrete sequence. How can you actually deal with this problem? People actually figure out that AlphaFold works really well with the soft lossy input, and you can actually optimize the gradient more better, like more in a stable way using the soft losses. So given a random like soft gumball noise or soft max of sequence, you can actually optimize it through the model, and at the end you can actually make it as a discrete sequence and optimize furthermore. So using this kind of concept, Minecraft this year showed this one-shot design of functional protein binders. So given a target sequence and template as an input, you can randomly initialize the sequence, giving a random Gaussian noise using an AlphaFold 2 multimodal. You repeat this gradient optimization multiple times, more than 100 times, and at the end you get this confidence structure and a sequence. So once you get this multiple structure, you fix the interface residues and redesign the rest part of this protein to make the protein to be more soluble, like using a soluble MPNN. And you make a reprediction with AlphaFold 2 monomer to cross-validate whether it's true or not. So filter out the designs based on the AlphaFold 2 monomer scores and also Rosetta score to ensure there are enough hydrogen bonds and less unsaturated hydrogen bonds. So we first try to use the same approach for this AlphaFold 3 models, but the key difference between the AlphaFold 2 and the 3 is it actually used a diffusion model for structure prediction. During the inference time, it usually requires 200 steps of this denoising step. What does that mean by that is if you want to backpropagate through this method, you need to backpropagate 200 times. It's really computationally heavy and it's very time consuming because usually the backpropagation takes longer than the forward prediction, so it will take really long time compared to the bind trap method. So we thought about the alternative way of actually optimizing this process. So we came up with the idea about this distogram. So can we actually use the pair features to optimize the structure in the sequence? Because the output of the pair feature Pairformer is a distogram, which is the predicted pairwise residue distance distribution, as you can see here. So you can see the intercontact and also intracontact, which is within protein contact information. And given this pair features and single representation as an input, diffusion model actually denoise the 3D coordinates. When you compress it into a 2D contact map, you can achieve this 2D contact map. And I just tested a few designs from the bind trap to see is there any agreement between these pair features and contact map from this 3D coordinates. And surprisingly, there's a really high the overlap and the agreement between the two features. So we thought, oh, if we are just trying to optimize the contact and the confidence, what if we just use a pair feature instead of using this full pipeline? So yeah, to check whether it's actually possible, we check the agreement between the Pairformer and the structure module. So here, as you can see in the left figure, if the Pairformer is not really good at predicting the correct ground truth contact for this bind trap designs, the structure module, the contact precision PK is also low. But if this Pairformer is really good at predicting the contact information, structure module is also pretty good at predicting the contact information. So you can see pretty clear this linear correlation, at least for these de novo designs. I think definitely it could be different for the natural designs, but we see very high agreement for this de novo designs. And as you can see in the right, we figure out the distogram contact loss can be a proxy for the predicted confidence. So in the left, the intra-contact loss is inversely correlated with the binder PLDT score, and in the right, interchain contact loss is correlated with the inter-PA score. So we can actually use the contact loss itself as a proxy of the confidence score instead of backpropagating all the way to confidence score and the distogram score. So yeah, our final model looks like this. So given a target sequence or ligand information as an input, we randomly initialize a binder sequence and input it to the model. So pair-trunk predict this pairwise information, calculate the contact loss for both within chain and between chains, and backpropagate this loss back to this pair-trunk. As an optional, we actually make this pipeline to backpropagate the confidence score back to this Pairformer, because I think sometimes there is a less agreement between the Pairformer contact score and the confidence score. For example, for more complicated DNA RNA interactions. So I thought, yeah, maybe getting a help from this confidence module is also helpful. But as a default setting, we always use this Pairformer, and then for the more difficult target, we are using both Pairformer and the confidence module. So yeah, this is the scheme that Martin actually made. So I just borrow his slide. So the overall like optimization is pretty similar to Minecraft. So starting with the really relaxed sequence, as you can see in this bottom, you're actually narrowing down into this like softmax and the discrete sequence like to get a one single good solution, right? After you get a like one hot encoded discrete sequence, you get the per residue level confidence score and like randomly mutate that positions that have a low confidence to other amino acid to purposely increase the confidence score of the sequence. So as you can see in the right, everything are started with a relaxed sequence. So you can see this orange, just like two alpha helical structures. And as you go more and more, like it actually wrap around this ligand and like, yeah, forming this like highly confident binding pocket. So we updated some experimental research because like we're collaborating with Martin, Flavia, Bruno from Bruno's lab. So we actually wanted to test some designs like for protein-protein interaction, but also small molecule binders and DNA binders. We couldn't get all of the research yet, but as a proof of concept, we designed like some binders toward this PDL1 proteins. So as you can see in this left, like 8 out of 10 proteins were expressed, and that we could confirm that like 4 out of 10 were actually showing a binding activity. We are like currently in the process of the actually calculating the KD value of this binder. And yeah, as you can see in the right, our design binder, which is the pink beta sheet binder, actually bind into this interface of this PDL1 and the PD1, like that can interrupt the interactions of this PD1 to the PDL1. So I thought, yeah, it's actually pretty cool. And then our method like can actually design a lot of like beta sheets, but also the alpha beta mixed proteins. So yeah, I'm really looking forward to get more experimental validation for the rest of the designs. And yeah, this is a new research of the FHBI binder. So this is actually the fluoropole. And there was a previously the approach that from the Baker lab, they designed this cool beta viral protein that can bind to the FHBI, a small molecule. And if this protein binds to this small molecule, it actually show the fluorescence activity. So it's really cool designs. And this is like totally the novo protein is designed with the Rosetta, like previous method like came out before the AlphaFold, probably AlphaFold 2 developed. So we also designed a binders toward this protein, and 10 out of 10 were expressed, but actually just 1 out of 10 just showed fluorescent activity. We're like thinking of the reason, why is happening like this? And then the key reason and our hypothesis of this is actually when we actually designed this binder, we didn't figure out, but after that, we thoroughly read through this like paper and we figure out, this small molecule needs to be like planar conformation to actually show the fluorescence activity. But we didn't really care about that like before when we designing this protein. So we thought, if it has a high IPTM score and like high Algina-Docu score, yeah, this is a cool design. So we submitted this design. But just 1 out of 10, this single design shows this like planar ligand conformations, but as you can see in this right, like most of the ligands are like kind of distorted, as you can see in this right? So I think, I assume that if we know this before, we can like definitely do the better job, but this is like pretty cool because like we can definitely, show this evidence to people. Look at this, like this fluoropole need to be planar to have a fluorescent activity, and this structure prediction model like AlphaFold 2 or 3 can actually correctly predict this conformation. So we are like still collecting this more in silico evaluation data sets. And Adaptive Bio, they also offer to design some binders. So we designed 10 binders for each of this target. So in the left side, we designed a binder toward this IL-7R alpha protein. They have both like 300 nanomolar KD value. And then as you can see in the right, for BHRF1 protein, we shows pretty tight binder, which has 2 nanomolar concentration. So yeah, this is a just brief research about our in silico evaluation. So when we submitted this paper, there was Earth diffusion all atom was the only existing model back by then. So we just like compare with this method, and we also benchmark 4 different small molecule ligands from their paper and like just totally randomly design everything with the scratch. So we could achieve like pretty high AlphaFold3 success rate, as you can see in the bottom in terms of like PLDT and the IPAE. So yeah, I definitely want to like check more designs experimentally, especially for small molecule, because I think, yeah, it's relatively hard to design like good binders for small molecules and like computational filter it out. Yeah, this is a summary slide for the BoltzDesign. So I think BoltzDesign is a really generable binder generation tool, and you can actually plug in this method to any kind of AlphaFold3 style model. So for example, yeah, because like this is just backpropagation based method, you can plug into AlphaFold3, Chai, like OpenFold, ProteinX, every different like kind of AlphaFold3 model, but we haven't really explicitly tried that from our side yet. So you can give any types of biomolecule as an input and initialize a binding sequence, and using any customized laws. Here we use like confidence score, the contact, intercontact, intra-contact laws, but you can use any kind of like customized laws you like. And we can also use a hotspot conditioning and the motif scaffolding, since the Boltz2 methods support the template, and also they have a like we can steer the diffusion models to actually condition some hotspots on the binder and the target. So we can, I'm still in the process of like developing this Boltz2 pipeline. And yeah, after you get the designs, you can design everything with the ProteinMPNN, LigandMPNN, either include interface residue or not. So you design everything and always like cross-validate with the other alternatives, AF3-Style models like AlphaFold3 and Chai. And I always like recommend to use other kind of like non like ML or more physics-based tool, because yeah, like you can definitely cross-validate more of your designs and remove more of like adversarial sequences. So for small molecule, we use Gina, and then for metal, we use this all metal 3D to actually check the 3D coordination between the metal on the side chains, and Pyrosetta to filter out the unset the designs that have a lot of like unsaturated hydrogen bonds, and like to achieve maximum like hydrogen bonds between the interfaces. Uh, but after I built this pipeline, I feel, yeah, it's really cool. We can really design very sophisticated interface, and the interfaces looks really cool because like compared to just ProteinMPNN designs, sometimes this backpropagation method makes really unique interface. Like, oh, so if you look by your eye, there are a lot of like very unique like hydrophobic dispersion interactions, but it often has a very low throughput. And then as a researcher in academic lab, it's really hard to maximize the number of like GPUs that I can utilize. So if you just use a one GPU, it takes like 10 minutes for designing one binder. And then like for designing 100 binder, you need to like at least spend one day to design everything. So I thought, oh, is there any way, a better way to accelerate this process? So yeah, I just made this like simple scheme to explain the difference of this different method. So as you can see in the left, this BoltzDesign method uses multi-step gradient updates. So every single step, you make a prediction, optimize the loss, update the sequence. So you're actually taking a really small steps until you're going to this actual solutions. So you need to repeat this like 100 to 100 times to optimize one designs. The good thing is like you can actually make a very cool designs that's not really easy to just generated by like any fine-tuning method, but it's actually taking a long time, and it's sometimes like stuck in the local minima, so it's really hard to rescue these designs. And as you can see in the right, the single diffusion trajectory method, like Earth diffusion, Boltzgen, usually they fine-tune the structure prediction model for designing purposes. So you can actually, generate the structure prediction in a one shot. And then like you sequentially design a sequence, like given this protein structure backbone as an input. But the problem of this is like the generated structure is not always like good. Sometimes you get a like suboptimal, not really great structure that has a low structure probability. Sometimes you can get a good structure, so it's kind of random. So to get a good designs, you need to actually draw like multiple prediction seeds to actually achieve the one good design. So usually they like in the Boltzgen, like they recommend to design 10,000 of designs structure and then redesign everything with the like inverse folding model, ProteinMPNN, or BoltzDesign inverse folding model, and then like cross validate with the Boltz or different AlphaFold style models. But yeah, this method is really fast. But if you generate the 10,000 of structured backbone, it actually also takes a same amount of time compared to this like gradient updates or like even more. So yeah, before talking about our new method, I want to like talk about more details why we actually came up with this new idea. So if you look at to the AlphaFold 3 paper in the figure 5, they show this comparison between this AF2 and then AF3 of disorder protein, the prediction on this disorder protein. So if you make a prediction on this like nucleopore complex, which has almost like 2,000 residues with the AlphaFold 2 model, you can actually predict the correct this disorder and like spaghetti-like structure, right? But if you make a prediction with the AlphaFold 3, it suddenly folded everything into this helical bundles of structures. So this is actually the hallucination problem because this is like not a ground truth, but it's actually making a false positive, but like generating a good looking structure. So in this paper, in AlphaFold 3 paper, they said, oh, they purposely fine-tune AlphaFold 3 model or own distillation set, which is composed of AlphaFold 2 prediction on disorder proteins. So they get a bunch of like this disorder protein and make a prediction with AlphaFold 2 and then like fine-tune this AlphaFold 3 model on this data set. So as you can see here, AlphaFold 3 actually can predict the spaghetti-like structure. So but when you look at this AF3 with no crystal distillation, they actually folded into this random structure. So people might say, oh, yeah, did we solve every problem? Because like we fine-tune it and it's finally like predict the right structure. But I think this problem is still like happening with the existence of the random binding partner. So as you can see in the left figure for this BRCA2 protein, if you make a prediction with the AlphaFold 3, it actually folded into this like this disorder protein structure. So which is cool. But if you put any binding partner, RAD55, the random binding partner, it does not like it's supposed not to actually make a tight interaction with this BRCA2 protein. It actually started to wrap around this protein and make this like very ordered helical structures around this like pink target, right? So we could still observe this hallucination problem. This is actually really bad for the structure prediction purpose, but we came up with this idea. Oh, what if like we just use it as a binder structure and redesign sequence that can actually fold into this structure? Because like in terms of protein design perspective, it's not bad to actually get a like good looking structure. Once we get a good looking structure, anyway, we can redesign everything, right? So we actually tested with this random kind of random amino acid repeat protein. So given this like target protein, we randomly generate this G repeat protein and give it to AlphaFold 3 like structure prediction model. Do you guys have any guess about the structure prediction? Yep. It actually looks like this. This doesn't look perfect, but it still like folded into some like okay structure and bind near to the protein, right? Then what happens if you just give a X repeat of proteins? Any guess? Okay. Yeah, it actually folded into this like very nice alpha helical structure and bind to the target. Yeah, we actually get this cool binder structure without any fine tuning, right? So we can definitely generate the PD1 binder in 10 seconds because like this whole process just requires the one step of the structure prediction. Oh, which is like still composed of like 200 denoising steps, but like just one for structure prediction from the end to end. So yeah, with this like 100 residues, like we can just generate anything in 10 seconds. So once we get this structure, we redesign everything with the ProteinMPNN sequence, give it a backbone structure as an input. But in a lot of time, when you make a reprediction with the AlphaFold 3 model, the IPTM are kind of like limited. They're not that high. Because I thought this one-shot design is not enough to actually make a good structure and a sequence and a good agreement between the structure and the sequence probability. Because as I mentioned in the like single shot prediction model, like diffusion model, Boltz and Earth diffusion, they need to like throw a lot of like random multiple seeds to get a one single good structure and sequence. So similar to that, we're actually not like folding the like ground truth like sequence into like good structure. We are like just folding the random. We're just utilizing this like this diffusion hallucination process like to actually just folding into the good looking structure, but they're not fully optimized because like if you input the all X residue, it never have like this complicated side chain interactions, and it doesn't have interaction. It just like gets something from the distribution of the protein. So it's still we assume that it's still far away from the good solution. So how can we actually solve generate a better designs? And then I think there are like previous mainly two previous paper that also adopt like this similar concept. So I'm gonna talk about this two method briefly. So in this AlphaFold 2 cyclic paper that is published last year, November, Frank and Sergey actually collaborated on this project together. So given this chroma structure and the sequence, they actually iterate this AlphaFold 2 prediction and redesigning with the ProteinMPNN process like multiple times to get a highly confident structure and a sequence. So how does it work is like given this chroma sequence, you make a prediction, you get a per residue level of confidence score and redesign the like positions with a low confidence, so giving a high weight of the ProteinMPNN logits. And then for the positions which is highly confident, you are like just maintaining the previous sequence. So after you repeat this structure prediction and then ProteinMPNN redesign, you can at the end you can get a pretty high confident structure. So as you can see in the right, compared to the gray structure, like which is the cycle 0 structure, and then pink structure, they are almost same, but the distance between the like the secondary structures and like overall global structure looks a little bit optimized. So they're not completely changing the structure, but still optimize the local structure a little bit, like to actually get a highly confidence structure and a sequence. Also, yeah, this LigandMPNN model they show, which is like pretty similar to LigandMPNN model. In this paper, they also show this joint optimization. So starting with this backbone and the ligand as an input, they redesign everything with this LigandMPNN, get the sequence candidates refolded back with the Rosetta fold method, and get the multiple of like structures and pick the best one that has a highest self-consistency and the confidence score, and repeat this multiple times. Here in a paper, like 35 times to get a one single good solution. So as you can see in this right, it's actually the joint optimization process because like you're predicting the structure and optimize the sequence and adopting that structure, new structure again and redesign and everything. So it's actually going toward a higher probability of the both sequence and the structure together. So we also use the similar approach here. Given a random amino acid or all X amino acid as an input, given a target, we utilize the diffusion hallucination, predict the structure with the AlphaFold 3 styles model. Here we use Boltz and Chime models as a proof of concept, and then redesign everything with the ProteinMPNN if this is a PPI, or LigandMPNN if this is like small molecule and then DNA, RNA, and then we actually iterate this like multiple times until we get a highly confident structure and sequence. So as you can see in the right, in the cycle 0, yeah, you can still get a like good, yeah, decently good structure, but if you repeat it multiple times, it's actually evolving and getting better. So yeah, we can definitely like introduce our protein hunter method, which is like exploiting structure hallucination within diffusion model for protein design. And this method is actually the multi-step diffusion trajectory-based method because like we're actually iterating this process multiple times until get a one good high solution. So this is relatively fast, but since you're co-optimizing the structure and the sequence together, at the end is like compared to this Earth diffusion Boltz method with a single cycle, 0 cycle, you can achieve the better solutions with the high IPTM or the PLDT score. So yeah, I tested multiple different like designing tasks using this pipeline, and then yeah, this is the result evaluated and then designed with Boltz 2 method. So as you can see in the left, if we increase this like cycle more and more for this unconditional generation task, which is just monomer designing task, we can achieve you can definitely see the PLDT is increasing like from the cycle 0 to cycle 5. And then when you compare the prediction of the cycle 5 from Boltz and then AF3's prediction for the cross validation, you can see the high TM score for this design protein. Because like if your protein is having a like bias for one just for one structure prediction models, like often AlphaFold3 is this model is like failing with predicting the correct structure. But if your structure is like confident enough and having a high probability of the structure, you'll definitely get a like more agreement between the Boltz model and the AlphaFold3 model. So as you can see here, there's still like a little bit drops in terms as we increase the length more and more, but there's like still a very high, relatively high agreement between the AlphaFold3 and the Boltz model. So yeah, we also evaluated our method on multiple of different like protein designing tasks, protein binder designing tasks. So as you can see in the left, we like chose like several targets from the Bindcraft paper and purposely redesign the binder for these targets. And then as you can see here, the protein hunter Boltz in the chai achieves a relatively high IPTM like compared to this Earth diffusion like the cycle 0 method and across a multiple of different targets. So as you can see in the right, we tested on the protein binders, but we also modified our pipelines to design a cyclic peptide. So by cyclizing the N terminus and C terminus of positional encoding together in a structure prediction model, we could also generate the highly confident cyclic peptide structure and sequence, and we could also achieve the binders toward a small molecule. One of the problem I've often see with this all X sequence-based structure prediction, the hallucination is if you input all X, in many cases, most of the designs are folding into this alpha helical structure. We assume that because it happening because X is actually used as a token that represent the unknown tokens from the PDB, but also known canonical amino acid, the amino acid. So throughout the training process, this X token is like used as a universal token. It never trained on like for the certain type of amino acid, but we assume that it probably learned the distribution of the protein. And as you already know, like in the PDB data set, there are a lot of like alpha helical structure compared to the beta sheet structure. So we definitely thought this is because like the X tokens learn the distribution and then most of the distribution is coming out from this helical structure. So we thought about, is there any good way to actually increase the structure diversity by like decreasing the amount of the helical structure, but increasing the amount of the beta sheet structure. So this is yeah pretty cool approach and also used in the BoltzDesign and the Bindcraft approach. So if you look into the contact map or the pairwise feature, there are usually very strong signals at position I and I+4 because those positions are actually making a helical like the structure, right? As you can see here, this position and this position is making a very tight interactions to generate these helical bundles. So what if like we purposely kill that signal in the Pairformer? So instead of like steering in the diffusion model, which usually like generate a very unstable structure, what if like we just kill the helical signal in the Pairformer, which is used as a prior of the diffusion model. So we did that, and that as you increase more and more the negative helical bias, you can see that there is a more generation of the beta sheet structure. So we are like still in the process of optimizing this for the binder because like it really works well for the monomers, but it's sometimes relatively hard to optimize for the binder because like there's also signal coming out from the target itself. So we're still in the process of optimizing this whole process. And I think, yeah, we can definitely do the simple designing task, but I think the more cool thing is like this binder designing toward this multimeric proteins and motif scaffolding, but not only just one motif, but also like conditioning of multiple different motifs that can interacting with the small molecule. So, and also partially redesign the CDR loop regions of the antibody. So we actually, utilizing the template information and like some of the modification, we could like successfully get some highly confident score for this multi-motif scaffolding designs and the partial redesigning task. So we are like currently experimental validating this multiple binding protein toward a TNF alpha and like some motif scaffolding problem. So I can summarize my method, and you can definitely utilize this method for multiple of different approaches, purposes. But yeah, as a representative like pipeline, I can like probably say this is the two-way that you can utilize these models and method. So the first pipeline is, as I mentioned, you can initialize everything with the all X or just random amino acid, or you can mix with X to actually increase more of diversity. And give it to the ProteinMPNN and redesign with the like LigandMPNN, ProteinMPNN multiple times until you get a highly confident score. But the other way is you can actually refining your own designs. So I think you probably design your like protein binders using a lot of like different method like earth diffusion, Boltz, right? So given that like modal output as an input, you can actually run this process multiple times to actually optimize the PLDT and the IPTM score. So Thomas in our lab actually performed this comparison between this Boltz method and the protein hunter method using this Boltz2 using Boltz2 pipeline. So as you can see here, we're still under the like experimental validation. So I couldn't really tell what is the target. So we just evaluated on one single target that Thomas is interested in. So we designed a binder, 3,000 binders using a Boltz pipeline, and then just 100 designs using protein hunter pipelines by randomly initializing the sequence using a mix of like all amino acid and then X tokens. And as you can see here, when we measure the IPTM, Boltz IPTM score, like most of the designs from the Boltz2 protein hunter are located in this like very high IPTM region, but a lot of like Boltz method are failed. And this is like kind of expected because in their protocol, they said, oh, you at least need to like generate the 10,000 of designs to actually generate the one single, several like good designs, right? So, but I think the even more cool thing is like, since Boltz can also like, you can generate the multiple different binders using a Boltz, and you can even like condition the fold and Boltz model. So what if like you get the Boltz structure as an input and redesigning everything with this protein hunter pipeline? So there was in the previous week there was a adaptive bio competition called like Nipah virus binder design competition. So we actually tested some design using our pipeline given a Boltz binder as an input. So we purposely took the structure that has an IPTM lower than 0.5, and throughout our pipeline we refined the structure more and more. So as you can see here, like there's not really many problem with the PLDT score. So at the cycle 0 they already have a good PLDT, but the problem is the interface binding, right? So by repeating this process we could achieve the IPTM, like the median from 0.3 to we can push it to 0.6. And yeah, that was probably the summary of like summary and the wrap up of my protein hunter. But I want to actually focus on more of like different stories from now. So yeah, throughout this adaptive bio, I've learned several like different things because I realized that structure generation and the designing is really cool, but the thing we also need to focus is how can we actually rank this design, and how can we actually filter out the bad design using an in silico confidence score or other kind of like physics-based method to actually increase the experimental success rate, right? So in this adaptive bio Nipah virus binder competition, they actually rank the design using a Boltz2 IPSAE score. So it's similar to IPTM score, but like using a cutoff like to calculate the IPSA score. So, and they purposely chose the 600 designs from the the top to the bottom. And then, yeah, they promised to do some experimental validation with this Nipah virus and like their design proteins. But I was like curious, what if like we make a prediction with AlphaFold 3? Is there any like strong agreement between the AlphaFold 3 and the Boltz score? So as you can see in this top, a lot of like Boltz 2 IPSA, the high IPSA designs are failed. So when you make a prediction with the AlphaFold 3, the IPSA is like really low. Oh, by the way, the 0 IPTA is bad design and the high IPTA is highly confident one. So yeah, this is like this is having a same scale with the IPTM. So there is no strong correlation. Like the sperma correlation is almost like a 0.3, and a lot of them could be the like potential false positive. And as you can also see in the right, there's like not really strong agreement with the AlphaFold 3 structure and the Boltz 2 IPTM score. So I made this website to actually show people, oh, the agreement between this AlphaFold 2 model and then AF3 model. And yeah, you can definitely re-rank it based on this AlphaFold 3 IPSA score and the IPTM score, and you can still vote on your best designs. And I think the deadline is today, so if you're interested, you can go into this website and vote on your best designs. If you want to like see the effect of the AlphaFold 3 IPSA like compared to the Boltz confidence score. So yeah, this actually makes me wondering, oh, then if you like just use the single like type of model, what if like my model like just achieves the high IPTM score and the IPSA score, but actually fail with the other models and actually not really generating a good experimental results at the end? So I thought confidence scores in a lot of like time, each model may be biased and may generate a lot of like adversarial predictions, as we can see in this like predictions. So for example, yeah, I assume if you take this like leftmost structure sequence that has a really high Boltz score but really low AlphaFold 3 scores, I think yeah, it actually fall into this like the solution one, which has a really like strong difference between the model 1 and the model 2. But I think if you get this sequence, like which has a high Boltz 2 score and the AF3 score, it actually, yeah, you can actually remove the effect of the adversarial sequences. This could be true or not, but I think, yeah, it's always like better to cross-validate it between the models and try to like filter out the bad designs, because like some models are highly overfitted or like biased toward some specific folds or like sequence. So we actually last week Sergey and I thought about, oh, what if like we just make a protein hunter to protein hunters, so to actually prevent the adversarial designs. So instead of the single-headed rabbit, we can actually make the rabbit as a hydra, so generate this like Boltz, Chi, AF3 ensembles like all together to actually design and optimize the binders. So instead of like taking a single step with the Boltz only or Chi only model, like what if like we just take a first step as a Chi and iterate second step with Boltz and iterate this process all together. So yeah, I think yeah, definitely if you incorporate more and more models, like you will definitely find less adversarial sequences, and you can definitely maximize agreement between all of these three different models. So yeah, my hypothesis is like, yeah, as I mentioned, if you use one single model, it's really easy to just adopt a good score for this with the single design. But if like there are a lot of like cases that are filled with the other models. But if you're iterating with the multiple models, you can definitely find a better solutions that can achieve the high score that has a high agreement between all of these different methods. So I actually, as a proof of concept, use this Chi and the Boltz model and iterate this two different models like every single cycle. So yeah, I still need to go through a more of like a thorough like computational analysis but at least with this PD1 target, initializing everything with the Chi models, I make a prediction, give it as to Boltz model, make a prediction with Chi again, so gray is Chi and the pink is Boltz. So make a prediction with Boltz again, Chi again, Boltz again, Chi again. So as you can see in this left, relatively Boltz model has a higher IPTM than the Chi, but you can still see the increasing like curve for both Boltz and Chi. just a little bit for Boltz, but try like from 0.4 to 0.8. So yeah, to summarize and like to talk about more of like key takeaways of my presentation is, I think, yeah, like, so including my models, BoltzDesign, Protein Hunter, nowadays, like there are so many all autumn protein generation tools existing, and there are like so many more to come out every day. Yeah, I'm a little bit afraid of like checking Twitter because like if the new model come out, I need to make a new comparison plot. So it's kind of like a lot of like burden to me, but I think it's actually really cool because like we're really focusing on the similar problem and we're like thinking about the better way to improve this kind of method. But on the other side, I definitely think we need to improve the filtering based method, right? As I shown, like there is not really huge agreement between each individual model, and if you're like just using this model like for generation and evaluation, it's really relatively easy to get a lot of like adversarial sequences. So I definitely think, yeah, we need more better like filtering method, evaluation method to design a better binder to boosting the experimental success rate. And also, like relating to this, the off-target effects remain a challenge because a lot of time, if you just design a simple binder and then redesign every sequence with a like ProteinMPNN, even though you can get a high confidence score, a lot of them like still have a lot of like LNA repeat, which doesn't really make sense, right? So, like as Sergey shown before, like what was the example that ubiquitin protein? If you mutate until you make a LNA mutation, like from 0 to 50%, you get really high confidence score, and then the folded structure looks exactly same, but after you like mask out or mutate more than 50%, like it actually folded into different structure. But that does mean that even though you make a like several like point mutation and multiple like a random mutation, it actually folded into the correct structure. That is the thing we definitely want to avoid. So I think we definitely need to think more about the off-target effects and make think about the better method to generate the very unique sophisticated interface. And the third one is, yeah, this is also the thing that I'm talking to myself, but instead of like just focusing on like more of like computational evaluation and taking the common protein targets data set as for computational evaluation and like experimental evaluation, I think that's also cool, but we need to like take more of like important real world protein design problems, try to think about what is the unsolved problem, what is the solved problem, and try to like figure out try to solve more of like cool and the real world problems. And then lastly, the future directions would be, as I mentioned, I want to like make this pipeline to generate the proteins that have more like dynamic like increase design diversities, and then I want to definitely leverage the collective intelligence across the different protein design method and tools. And finally, we're like continuing expanding this protein hunter and BoltzDesign with more design modes. So not only just for the binder to single binder, but yeah, we'll be definitely coming up with a more of like different playful protein design challenges. So stay tuned, and we have all the code bases in our GitHub. And you can also easily, yeah, redesign everything with the Collab Design Notebook. So finally, I want to like say thanks to our collaborators. The first row is like who are mainly involved in this BoltzDesign pipeline, and the second row like who are mostly involved in this Protein Hunter pipeline. So Martin, Flavia, Bruno, and Tudor from Adaptive Lab, and then yeah, my advisor, Sergey Guru from IPD, and the Griffin, Kathleen, and Tomas from our lab. And also I want to thanks to Nano Banana who generate all of this like cool, like nice bunny figure for me. So yeah, I spent three hours yesterday to generate the more better figures for representation. And I also generated this figure with Nano Banana. So I got some inspiration from the last week MLSP conference from someone's slides. So I generated it by myself. Oh, not by myself, by Nano Banana. And then yeah, they just like name it put the random name, so just ignore it. And then yeah, the other like Celeb members. So I really want to thanks to Celeb people and then my PI Sergey. Thank you. Oh, question.
Why do you think that Boltz two is so confident.
Oh,
Is the
Yeah.
confidence model trained differently than an AlphaFold 3?
I think the confidence module, I heard that it's more different. Like it uses more like much more that like parameters and the layers compared to the AlphaFold 3. And then compared to AlphaFold 3, it reinitialized AlphaFold 3 trained the confidence module from the scratch, but if I remember correctly, the Boltz initialized the confidence module weights from the Pairformer. So there's like some information from the Pairformer kind of like linked into the confidence module. That was one of my hypotheses, but not really sure about it. Yeah. So it reinitialized the weights from the Pairformer. Question.
Oh, somebody back.
You mentioned KD several times.
Yeah.
How do you calculate the KD and then how do you validate those calculations?
Yeah, so actually, the way they measure the KD is like using a BLI. So given a different the concentration of this protein binders. So by immobilize the target on the BLI surface, and then like you vary the concentration of the binders and get the curve, equilibrium curve, and like calculate the KD. Oh, I don't exactly right, measurement. Yeah,
How do you calculate?
calculated. Okay. That's a good question. Yeah. I wait. Okay.
Like an exam question.
Right. That's a good question.
It's not from the Boltz 2 model, right? Which does have this equilibrium curve and then C converted back to KD, which is an estimate of KD, not necessarily.
Oh no. KD is experimental value, so I measure it by the experiment. Yeah. I haven't done by myself, but this is from my collaborators. Yeah. But I think this is like the equilibrium, so you can definitely get from the complex concentration, which is like coming out the BLI signal divided by the reagent concentration and the protein concentration. Yeah.
Or what are there any models that calculate?
Oh,
We predict.
They calculate it, but
okay. I think there is no so far. I don't know any of like that model that can calculate the KD.
isn't that
Computational.
challenge then for the field? You're talking about.
Oh, I think
Don't you want to know how much they bind?
Yeah, I think there is like some.
Just to say that bind, doesn't bind. It's useful.
I think there is like some couple of ways that like fine tune like Boltz-2, including Boltz-2 for small molecule, and there are like some like GNM based method or other based method that purposely fine tune like protein KD value like a SCAMP, which includes a lot of like mutations based KD value. So they are like try to like just predict the KD value like from the scratch, but I don't think like they're so far like really great enough like to cover all of like different like dynamic proteins and like very difficult target the KD for very difficult targets.
In the Boltz 2, it's able to predict KDs for all molecules to proteins, but not for protein.
Not for protein.
Not for protein compound.
Yep.
Not there yet. They have some kind of classifier, but it's not yet the delta G or KD predict.
Yeah, question.
So I'm wondering if binders generated with a higher helical loss have lower experimental accuracy.
You mean lower experimental experimental accuracy?
Yeah, because right, there's bias in the model, and that's why you have to apply this helical loss.
Got it.
But because you're doing that, does it mean that the binders generated are lower, less likely to be successful?
Yeah, that's a question. I don't really have enough like data points, so I can't really tell. But I think for our designs, we at the end we try to like roughly filter out like everything based on like Rosetta. So delta G and also the number of hydrogen, unsaturated hydrogen. We are trying to maximize the like specificity by making a like very specific like bones. So I think, yeah, that probably helped to increase the experimental success rate, but I don't really know about that correlation. But yeah, there is a really cool protein database called ProteinBase for adaptive bio. They like compile like more than 3,000 data sets from all of this like different types of model, Minecraft, BoltzGen, BoltzDesign, everything. So you can definitely like get some design from that and like correlate the like KD value or the affinity, yeah, between like the specific types of binders versus the other.
Really cool method. It seems super efficient.
Oh, thank you.
So in the cartoon, you have it kind of jumping like equal steps.
Yep.
As it like gets to the
Mhm.
binder or whatever.
Mhm.
Binder.
Uh-huh.
Have you looked at the sequences? So like if you do an alignment between like the different cycles and
Uh-huh.
like you look at how much changing every step.
Yeah.
Like just based on the IPTM, it seems like it kind of saturates
Uh-huh.
quickly.
Uh-huh.
And maybe that makes me think the like changes are small in
Uh-huh.
later cycles.
Uh-huh.
But like, have you checked that? And if you have, like, are the changes at the interface,
Uh-huh.
not at the interface?
Uh-huh. You mean the changes like
The
in
mutations.
Oh,
if you do
mutations.
alignment.
Yeah, that's a good question. I haven't really tracked the changes in sequence like compared to the IPTM. But yeah, as you mentioned, definitely there is like you can see the saturation of IPTM at the later stage of the cycle. So yeah, I think they're like definitely going to be like something differently compared to the cycle zero. But what I feel usually is like as you getting more and more of the cycling steps, you get more of like confidence structure. So I think yeah, there's like at the first tab, like there are a lot of like different room to be improved, and they're like if you redesign with a ProteinMPNN, a lot of like sequences are very different. But I think at the end like slightly converges. But I haven't explicitly calculated the sequence identity for that. That's a good suggestion. Question.
Thank you, Doc. And this is somewhat related.
Yeah.
You kind of alluded a little bit to the alanine content. I saw that in your program, as you go through the cycles, you basically change the bias.
Oh, yeah.
Could you just elaborate a little more?
Yeah. Right. Yeah.
What you're thinking is, and why there's this seems to be this why you need to change the alanine
Right.
bias.
Yeah.
Because I've noticed with you that ways.
Right. Yeah, we included alanine bias as optional because like we frequently observe that if you redesign everything using X tokens, a lot of like token residues are redesigned as an alanine when you redesign everything with the ProteinMPNN. The reason is like the X shares the same like side chains with the alanine in Boltz model. So they use a C alpha C like NO C beta like 5 atoms. So I think if you fold it into the structure, it actually replicate a lot of like similarity with the alanines, right? So yeah, at the very early stage, yeah, I frequently see that there are a lot of really high percentage of alanines. So I thought, oh, what if like we just purposely penalize the alanines for like all the residues, so just decrease the alanine. But at the end, I didn't really want to bias the model and like generate the sequence like with a certain bias. So like maximize the alanine bias at this turn and then try to like remove it a little bit. So at the end, like, yeah, you can probably, design everything with the like last bias.
I have a question. Thank you so much for the talk. I noticed that there are recent studies showing that the co-folding structure prediction models might be memorizing a little bit instead of actually understanding the like, physical processes.
Yeah.
So do you think that might affect, for example, the performance actually dependent on the target? For example, if you perturb the target, are the design still robust, or if you predict the design of binder to a de novo protein, does that?
Yeah, I think definitely. Yeah, I think I agree with that. So as you can see in like few like different examples, like some of the models have a really like high IPTM score, like with any kind of like just generate binders, but some of the models like have really low scores. And then it's actually not like consistent, like it's really varied by the like target by target. So yeah, the reason I suggested like, oh, what if like we iterate the multiple different method is like to try to like see the agreement between different method. So I think that could be also like one potential like approach to solve that. But I don't know like 100% sure why is it actually happening. Yeah, because like all of the different models, like training in different ways, yeah, a little bit different data set, like a little bit like different like layers and parameters and everything. So yeah, it's definitely also depends on like how you initialize the training weights when you train this model. So yeah, the thing I really like about the AlphaFold 2 model is like you have 5 different models. So at the end, you can iterate all of this model to see the agreement between these 5 models. So I think the Minecraft really works well because like you have 5 different models. But I think in this case, like we are just having a one single model for each different method. So it's kind of like hard to tell like which model is actually telling me the truth. But I think, yeah, definitely assembling the model could be a better option.
Well, thank you very much.
Yep.
Yeah, I have a question regarding options. So I think that these methods are very good at creating the binders. And you were showing an example of PD1 and just reminding that there are reports where antibodies have been generated against PD1 and depending on where they bind, they might elicit in the end either agonistic or antagonistic effect. So how biased are these models into generating binders that will act in a single functional way? Like if you were now to give PD1 to your Boltz or your method, how many of those binders will be agonists or antagonists, and how much freedom these models have to explore different regions that are outside, the region that the PDB, the region of complexes that are positive PDB files and that may have a different functional output.
Right. Yeah, that's a really good question, and definitely it has a bias because like if you give a random like X tokens, I frequently observe that it actually binds to the binding pocket, known binding pocket. So model like definitely have some bias toward the certain interfaces as you mentioned, right? Like throughout this like training process, I'm not sure like whether it's like training problem or overfitted problem or it's actually very clear like the binding pocket. I'm not sure about like the answer, and it depends on the target by target, but definitely there's if I run all X like 30 times, like in most of cases, it binds to the very clear, like the certain binding pocket. So I was like also thinking about like, what if like you give a multiple of like X sequence? So instead of like giving an X binder, so let the model to figure out the alternative binding site by competing with each other. So all like for example, 10 of all X sequence and then like just one binder. In that case, I've observed like this binder bind to this, but the other binder bind to this other position. So maybe we can like get a cool like statistic using it, but not sure like what is the best way to actually diversify the interfaces and binding pockets.
So it's saturating the target.
Yeah, saturating the target. Yeah. So if the like number one is occupied, like what is the next positions that model like we're gonna like put the second binder?
That's nice.
Yeah, thank you.
I think we'll do one last question for someone online.
Yeah.
So somebody named Min Chen was asking about D protein targets and whether or not it works for D target proteins. And she also mentioned something about AlphaFold 3 being very, very confident for D proteins, and if that's going to be a problem.
Okay. Yeah, deep protein targets. So I try to like utilize the Boltz 2 or Boltz 2 method to predict the structure of the deep protein, but a lot of time it doesn't really correctly predict the deep protein. So like I personally explore a little bit designing a D like mini binder or peptide toward this protein of interest, but the way that encode the D protein is a little bit different. Oh, but I think I recently made like some pipeline for the D amino acids cyclic peptide. But definitely, in summary, I guess, these D protein structure are like somewhat limited, I guess, in many cases, even though like there's a certain like structure in the PDB and it's not really exactly the same with the mirror image of the L protein. So I think there's still a long way to go. And then I'm trying to like see, is there any good way to condition these structures for L binder designing or both like D binder designing? That'll be like cool approach.
We have one last
Yeah.
question, and Sergey said that was the last question.
Right.
Thanks. So let's say that I want to design a binder. That you laid out 3 strategies.
Yeah.
One of which is protein hunters, which you sort of identified as more efficient than something like art diffusion, but then less efficient than something like Minecraft. So which of those 3 would you recommend I use?
Yeah.
Like in which contexts want to use one over
Uh-huh.
the other, but how do you tell?
Uh-huh.
Oh, this is a situation where you
Got it.
use Minecraft
Mhm.
versus using.
Yeah. I think if I say one is better than the other, I'm kind of like killing myself. So I'm not gonna say one is better than the other, but each method has their unique property. I say, like the BoltzDesign Minecraft, like you normally like fix the interfaces and redesign everything with the like LigandMPNN. I think like sometimes we really frequently observe the uniqueness like coming from the interfaces itself. And Martin, my collaborator, I asked him and he said, there's like something going on, like, and then like there's more information like coming out from the by inverting this structure prediction model. Like they are trained a more enriched data set, like MSA data set, more like structured data set, like compared to this like very simple inverse folding based method. And sometimes like you can frequently observe that this ProteinMPNN, LigandMPNN just generate the very simple sequence that actually fold into this structure, but we are not like, we can't really guarantee this is like highly specific or not. So I think, if you want to like focus more on like interface versions, like definitely, I recommend this kind of like more of like co-design method, structure, Minecraft and BoltzDesign. And if you want to really accelerate everything, like just you want to like generate the 1,000 data set, and I'll just filter out and get the best like based on the confidence score, computational score. I think by definitely merging this single diffusion trajectory method of diffusion Boltzgen with this protein hunter method, LigandMPNN, and then alpha 2 cycler method would be the best way because with a few number of seeds you can like maximize the confidence score and then like maximize the joint probability of structure and sequence.
All right, let's thank you again.
Thank you.